Hey everyone, it's Ken. I want to tell you in this video what's the definition of concave up, that's a function opening up, concave down, that's a function that's opening down, and I also want to tell you the definition of an inflection point. So formally what this means is, say that you've got a function, we'll call it f, and I'm going to say that this function is concave up if the derivative f prime is increasing. And the classic example of a function that's concave up is, let's look at f of x equals x squared. Nice parabola, it opens up like that. And its derivative, so this is x squared, its derivative then is going to be 2x. And if you look at 2x, that's certainly an increasing function, no doubt about that. So in general, whenever your derivative is increasing on an interval, then we say you're concave up on that interval. There's another way to test for that. So in a previous video, we've seen the mean value theorem. We've seen that if the derivative of a function is positive, then that function has to be increasing. The derivative of the first derivative, that's the second derivative. So in fact, another way to think about this is that if the second derivative is positive on some interval, then that's the same thing as saying the first derivative is increasing. That's the same thing as saying that you're concave up. So like a schematic picture, in this case the second derivative is just equal to 2. But the schematic picture in general, your second derivative bigger than 0 means your first derivative is increasing. That means your function is concave up. Now, if you want to define concave down, it's just the straight reverse of that. So second derivative would be negative. Come down here, draw a schematic picture. Let's just use negative x squared. So the second derivative would be negative 2. And then if your second derivative is negative, that means your first derivative has to be decreasing, right? Because once again, if the derivative is negative, that function has to be decreasing. And if your derivative is decreasing on some interval, that means your function has to be what we call concave down, and that's minus x squared. And so this first one is concave up. The second one is concave down. And these graphs that I've drawn, they're concave up and down on the entire real line, on the entire interval from negative infinity to positive infinity. But it is true that you can switch from concave up to concave down. You can be concave up sometimes and concave down other times. The easiest example of that is if I look at, say, let's take y equals x cubed. Here's the graph. It looks something like that. And if I look at its second derivative, here's its second derivative. So the first derivative would be 3x squared. The second derivative would be 6x. So notice the second derivative is positive whenever x is bigger than 0. So that means you're concave up on this interval from 0 to infinity. The second derivative is negative whenever x is negative. That means you're concave down on this interval from negative infinity to 0. And the place where you switch from concave down to concave up, or from concave up to concave down, that's what we call an inflection point. So your x value, in this case the inflection point is 0. Your x value is an inflection point if that's the place where you're switching from concave up to concave down, or from concave down to concave up. And so one way we know to test for this now is you can look at that second derivative. If your second derivative switches from negative to positive or from positive to negative at a point, That's telling you that you're at an inflection point. So that's all about concavity and inflection points.